You know, we talk a lot about generating more and more renewable energy, but what if the next giant leap forward isn't about making more power, but about cleverly using the power we already waste? Today, we are diving into a really cool piece of technology that takes a huge problem for renewables and turns it into a super valuable opportunity.
It sounds like a great problem to have, right? But here's the crazy part. When the sun is shining bright and the wind is blowing hard, our clean energy farms can actually produce way more electricity than the grid can handle at that moment. And when that happens, grid operators have to do the unthinkable. They just shut them down. All that perfectly good, clean power, it just disappears. Wasted. And this gets us right to the heart of one of the biggest challenges for renewables. See, unlike a gas plant you can turn up or down, you can't just tell the sun to dim a little or ask the wind to take a break. This oversupply creates what's known as the paradox of plenty.
The official word for this is curtailment. It's a pretty gentle term for a harsh reality, which is basically throwing away clean energy. In places with a ton of renewables, like West Texas, this happens so often that electricity prices can actually go negative. Think about that. We're not just wasting energy, we're wasting billions in potential revenue. So, how do you possibly fix a problem like that?
Well, the answer might lie in this brilliant concept, a power sink. Now, this isn't just any old factory. It's a flexible facility specifically designed to soak up or, drink all that excess, nearly free electricity from the grid.
This quote from the inventor, Dr. Robert Odle, just nails it. Instead of seeing all that extra power as a problem to be managed, you start to see it as a resource. You're not just dealing with waste, you're actively converting it into something incredibly valuable. In this case, high-grade magnesium metal.
So picture this, a factory that absolutely loves cheap, abundant electricity. You design it to be super flexible so it can ramp up production the moment the grid has too much power and prices plummet. It essentially becomes a giant shock absorber for the whole system. It's not just a factory anymore, it's a vital piece of grid infrastructure. But here's the really fascinating part. This isn't some brand new, totally untested chemistry cooked up in a lab. The inspiration for this process actually comes from a technology that was developed out of sheer necessity during World War II. It's an amazing story of old-school engineering getting a modern, high-tech makeover.
Back in World War II, this plant, the Permanente plant, was built to churn out magnesium, which was a critical material for building aircraft. And the process worked, but it had one major flaw in peacetime. It was a total energy hog. That made it way too expensive to run once the war was over. And here's the beautiful irony. Its biggest weakness then is its greatest strength now.
The original plant's whole problem really boiled down to its cooling system. It used this massive, inefficient blast of natural gas. The modern innovation is to swap that out for a tiny, super precise spray of a liquid coolant. This liquid instantly vaporizes in a controlled flash, and that rapid, almost explosive expansion is the secret sauce for the whole new process. Okay, let's get into the details of how this modern process actually works, because this is where some seriously cutting-edge science completely transforms that old, clunky method into something that's sleek, green, and incredibly effective.
All right, let's walk through it. It starts with a super hot reaction that creates magnesium gas. Then, and this is the magic part, a tiny bit of liquid coolant gets injected. It immediately vaporizes, flash cooling the gas into solid little metal particles. Those particles get filtered out and, get this, both the coolant and the carbon monoxide byproduct are captured to be used again. Almost nothing is wasted.
To really get a sense of the power we're talking about here, look at this number, 170 times. That is how much the liquid coolant expands in a fraction of a second. This isn't just gentle cooling. It's more like a controlled micro-explosion. This violent expansion is what makes the whole thing so incredibly efficient, and it's what stops that valuable magnesium gas from just turning back into its original ingredients.
So, what's the payoff for all this clever engineering? Well, the patent outlines 3 massive benefits. It's a genuine triple win for the grid, for the economy, and for the environment.
First up, grid stability. By acting as this huge, controllable customer, the plant literally drinks up that surplus power when the grid is overloaded. This directly cuts down on wasted energy and helps smooth out those wild price swings that can make renewable markets so unpredictable. Second, there's just a powerful economic argument here. This process takes an input that's extremely low value, surplus electricity that can sell for next to nothing, and transforms it into a really high-value product, magnesium. That's a critical metal for huge industries like automotive, aerospace, and electronics.
And finally, the sustainability win. This goes beyond just helping renewables. The process itself is designed to be circular. It captures its main byproduct, carbon monoxide, so it's not released as a pollutant. Instead, it becomes a valuable ingredient that can be used to create next-generation synthetic fuels, effectively closing the loop on emissions.
Now, this all sounds fantastic on paper, but how does an idea like this actually move from a patent document to a real, functioning industrial plant? Let's take a look at the next steps.
The next big step is to prove this works at scale. The inventor estimates that a pilot plant would cost somewhere around $20 million. And that's really the first major hurdle you have to clear on the path to making this a commercial reality.
And that's where the investor ecosystem comes into play. Right now, there is a massive amount of capital out there actively looking for these exact kinds of projects. You've got everyone from early-stage venture capitalists to huge infrastructure funds, and they are all hunting for transformative ideas that can help decarbonize heavy industry.
And this really points to the long-term potential here. This innovative cooling process isn't just about magnesium. The same core principle could become a platform for producing other critical metals, like zinc and manganese. It could potentially revolutionize green metal production across the board.
So when you step back and look at the big picture, this is way more than just a new way to make metal. It's a whole new way of thinking. It reframes what we consider industrial waste into a strategic asset. And if we can turn wasted electricity into a solid bar of metal, it really makes you wonder, what's next? What other massive industries are just waiting to be reinvented for the clean energy era?